on signing the sheet up there. You did well. Some of y'all didn't put y'all's number up there. But part of the number, right? So, and I think the biggest problem we had was that detailed operation of the circuit. I think we're looking at directional control valves. Y'all got any questions on these? Yes or no? As far as running actuators, we can do anything with a fluid power circuit that we can do with electrical. Huh? This is just a continuation of the last lecture on directional control valve. I don't know how it's laid in the book, but it's whichever chapter is directional control valves. I think it's chapter 2. Shuttle valve. Are we okay on shuttle valve? Y'all understand that? Shuttle valve. So with electrical, we can do what we call logic. Anybody know what logic is? When we start talking about logic, what are we talking about? So we have basic logic functions. Anybody know what they are? No, that's not logic. That's digital. We have what we call and you're supposed to write these in uppercase letters, and that way you can use or. No, that's not a lot. That's a combination logic function. Yeah. These are the basic logic functions. Five. So in logic we have 5 basic functions, and then we use these 5 basic functions to create all types of functions. So a exclusive OR and exclusive NOR is actually a combinational logic circuit. So you combine functions to get that. So this right here would be what a shuttle valve does OR. It's an OR logic. So that means I can create an output if I put a pressure on port 1. I don't know why they call that one on the other side. 1 on the left or 1 on the right. It's going to automatically shift that little spool in the center and cause the output to be true, have pressure in it, right?
Oh, you're saying that when you push from one side, it closes the other side?
Yeah, we'll see. Here's the animation. If it'll animate, yeah. So this is a, now if it's already shifted over to the left, and you put that pressure on the right, and it's the same pressure source, then the pressure will be equalized and it won't move, right? You understand that? So it means if I do put pressure on the left-hand port 1, and it's sitting over here on the right-hand port 1, the little shuttle valve is not going to move. Because why? Because the pressure is equalized on both sides. So what we're saying is if I put pressure into the left port or the right port, then port 2 would have pressure on it.
Okay, what's that thing that you mentioned with that's a check valve?
No, that's the little shuttle that's moving back and forth. So you can't say it's a check valve because check valve will let pressure flow in one direction. Both these are letting pressure go out of port 2. Period, right? You understand? Okay. So we're not saying port 2 only flows in one direction. But what we're saying is that I can get pressure out of port 2 if I put pressure on my left port 1 or my right port.
I'm looking at it, I'm going like, what would be the purpose of switching sides when you're only going out one port? You know.
The example we gave is I've got a big press that puts out 5,000 pounds of pressure, and I've got 2 operators out there. And I don't want the second operator to screw if I've got that sucker up, I don't want that second operator to have the ability to bring it down. So as long as I've got my hand on this button right here, that other operator can beat on that sucker from now to doomsday. All he's doing is making the other port true, but when he goes false, 2 stays true, right? You understand? So we're saying, okay, I've got 1 or 2 could make the press go up or go down, but the other one's not true, right? You understand that? Yes or no? That makes sense. So you see these used a lot, and that's one of the big things they do is where we can control something from 2 different stations, but one station, the one that hits it first, controls it, and the second one can't do anything to the first one. So it says 1 or 1 gives me a 1. That would be digital. What we use is any. So in digital we teach any. For or we say any. If pressure is on any port, we would have pressure on the output. The only way I'd get pressure off is if there was no input, right? And this would do what we call OR logic. How would we make it do NOR logic? Well, you got to understand, how would we make it do NOR logic? Well, you just got to think about it a little while. We can't do NOR logic. So even though it's not like this, this would be in logic. This would be the symbol of a NOR gate. But some people learn it like this, which is not exactly correct, but it makes it a little easier to understand. I should have because I can't. Let me run the program. So the logic symbol for this guy would be this right here. And that's the logic symbol for OR function. That's an OR. And then we have this thing called an inverter, which has that symbol right there. Well, I can come up here and do this, and both those together would generate what we call a NOR. But the actual logic symbol for a NOR is this right here. So what I can do is I can take my shuttle valve. Y'all understand this? And then I can run it into a second valve. And then this would be a pilot operated valve. Okay. And then what we would do is this would be this one. So we'd have a normally open valve. And then over here, this would be closed. And then my pressure comes right here. So right now, with my shuttle valve being false, there's no output. Then it would be letting the air flow, right, or fluid flow. When my shuttle valve shifts, it's going to shift it over, and it's going to cut the valve. It's going to cut the air off on my second valve. So here's my NOR right here. It's the combination of both those to get what we call a NOR. So here we're saying I get pressure on my actuator if neither one of my inputs are true. If I don't have pressure on either of my inputs, I have my actuator got flow to it, right? You understand? And if I put flow into either one of these ones, it's going to shift my normally open two-way valve over there, or two-position valve. It's going to shift it over and cut it off. So this would be a NOR. Yeah. So this would be, this right here by itself would be an OR, but I take it out and invert it with a normally open valve, and that turns it into a normal. So that's two logic functions that I could do with digital.
It seems like we're doing anything.
I don't know what you mean.
Oh, so you're saying when the first one?
Yeah, well, this guy is not showing. This guy is showing what the simulation is showing. It's not showing if I don't put pressure on either side. If I don't put pressure on either side, then there's no output on two. Okay, so I don't put pressure on either side, and my normally open valve would be shifted over, and my actuator would have pressure on it. But when I put a pressure on my port 1 on the left or port 1 on the right, it's going to put pressure, and it's going to shift it all over to the closed position. And it's going to shut off pressure to the actuator. So what we've done is we've created a NOR, a 2-input NOR. And how would I create 3 inputs? That's what's so neat. So I could come up here and have one shuttle valve. Of course, it takes a little more work. So I could have one shuttle valve. Okay, and then I could have this feeding the input of another shuttle valve. And then this would be this guy right here. That would be a 3-input. That would be a 3-input invert. That would be a 3-input OR. So we can, so in digital, good gracious, we can have up to 8 inputs on a single OR gate. Actually, you could have more than that. That's the biggest one I've ever seen. What we would have to do is we'd have to stack these. So if I wanted 4 inputs, then I'd have the output of this one feed another shuttle valve, and then bring in that 4th output. So we could stack these things and basically have a big OR. And then I take the last one and run it through a normally open, and then I would have a multiple input NOR logic. So a shuttle valve, what does it do? It does OR. If I needed a NOR, I would take the output of a shuttle valve, run it into a normally open a pilot valve with spring return, and that would give me a NOR. No, the flow control would be the flow control is at the cylinder. So if you're going to control the speed of the cylinder, then you would control it at the cylinder. You wouldn't control it at the valve that's actually doing your control. So I can show you all kind of diagrams when they control the flow, and they don't control it at the valve, they control it at the cylinder. That makes sense. So all these guys are just giving me what we call a digital control. We don't have time and we don't have the equipment, but we have what they call proportional flow control valves, which basically you can electronically control. So our flow control valves, you're going to have to turn a knob on them to set the flow. But if you can turn a knob, I can do that electronically, right? You understand that? So we have what we call proportional flow control valves. We have proportional valves, directional control valves, which not only control the direction, they also control the flow. And so we could actually control the speed of cylinders electronically. We used to have a setup downstairs, and we got a valve over there that's got the setup on it. We had some proportional flow control valves downstairs, but they were for hydraulics, and we don't have that. We don't even have flow meters. So it would be impossible for us to try to even calculate the speed, because you can't calculate the speed unless you know what? The flow. And we don't know the flow into the cylinder. So how would we do AND? Can't do AND with this guy. So we got another valve that's part of our kit called a dual pressure valve. And let me bring up, and it's not in the PowerPoint slide, guys, but we got it in our unit over there. And I don't even think, the book covers the shuttle valve, but the book does not cover. In this animation that I got this off the internet somewhere. These are what we call animated GIFs, but it don't show you what happens when you don't put any pressure on port 1 or port 2. If you don't put any pressure on port 1 or port 2, then port 1 or port, they got them both labeled 1. We'll look at the actual labeling on them. right now I say left hand and right hand. If I don't put pressure on port 1 on the left or port 1 on the right, then port 2 has no pressure. So when we say or, we mean we got to have pressure on one of those ports, right? You understand? So what would I do? What would I do with an and? Yeah. So here we're talking about pressure, right? If we had 2 inputs, but we could do the same thing. We could do the same thing with a that we did with the shuttle valve. So what we have is we have what we call a dual pressure valve. Yeah. So this is a dual pressure valve. And this should be, so this is my out. And these are my 2 ends. We call it N1 and N2. We'll have to look at that. Can y'all see how that works? We got these over in the drawer over there. So let's say I put pressure on this side. What's it going to do? It's going to call this spool to come over here and it's going to block it off. And I'm not going to get any output pressure. Right? If I come over here and put pressure on the other side, what's it going to do? It's going to come over here and block it off, and we're not going to get any output. Y'all understand so far? What's going to happen if I put pressure on both sides? It's going to equalize out, and it's going to go into the position that's shown. If I put the pressure on both sides, then it's going to do, and of course, what's going to happen? Now we're going to get output. So here, both the inputs have to have pressure before you get pressure on the output. So here we'd say all inputs have to have pressure to get output. And this is an AND. Now in logic, we would draw this symbol like this. In logic, we would draw the symbol like this. So it's the shape of a D. And that would be AND. A NAND symbol, logic symbol, would be like this. And that means the output is inverted. So what would I do on this one? I would do exactly the same way to get a NAND. So I'd come over and take this out, and I would run this into a normally open pilot operated valve. So if I call this A, and I call this B, and I call this Z, then if I didn't have pressure on A, if I had pressure on A, I wouldn't get anything out of 2, right? You understand? And it would be over in the right position, so we'd have fluid flow to our actuator. If I put an input on B, then I'd have fluid flow. If I didn't put an input on A or B, then it was still center, and I'd get output, right? You understand that? If I put it on both A and B, then we have flow out of 2, or Z, that would push that valve over and stop it. And that would be a name. And then if I needed 3 inputs, I would just take the output of this one and feed it into the input of another dual pressure valve, and get 3 inputs, and we would stack them just like we would oil. And by the way, this is a knot right here. So this is a knot right here. So it's real simple. We've run into a knot before. So a knot is nothing but a normally open valve. That's all it is. So that's a knot. You understand that? If I don't do anything to it, the air flows. As soon as I put pressure on that side, the air cuts off. So that's a knot. That's a knot. This is a what? That's an and. So if I combine an and, if I take the output of an and feed it into a knot, I get an and. And then this right here is a shuttle valve. And this gives me a what? Or. So if I take the output of an or, send it to control the knot, then I get an or, right? You understand? If I take the output of the and, let it control the shuttle valve, got to tell it. Then I've lost my train of thought. So y'all see how we get the 5 basic logic functions? And when you talk about digital, I don't care what you got. In digital, whatever you got in digital comes from these 5 basic logic functions. I think the text gets more detailed than this. They show you how to actually wire stuff up. But, I don't know why we would do that when we've already got an and an or out there that we could purchase. It would be like me trying to build a NAND gate out of transistors. And you can do that. Why would I do that when I can buy NANDs and NORs and NOTs? And sure, got any questions on that?
Real quick, are there like 5 basic like units, like we put up the units on the wall that represent the knot, so I can go in there and I can find one of those.
You can go in there and you got shuttle valves. We got shuttle valves in there. We got dual pressure valves in there. So we got I don't know if we got any normally open valves. I think all ours are. I think the smallest valve we have is a 3-way valve.
They put the 4 on the end of the knot to get a door.
What?
No, I'm trying to.
So this is a knot. So if I take this and this is an or, and then I come up here and I look at this, this is a nowhere. Well, that right there is nothing but just taking the output and inverting. So what we're saying is I take the output of the and then I run it into a normally open valve. So what I've just done is I've just did that right there. I've added that inverted output. So that means if I come over here and I don't put anything in on A or B, then this is not shifting that valve over and air is flowing through that valve right there. Right? When I put B, it's going to be shifted, air is going to flow. When I put A, it's going to be shifted. It's going to shift, air is going to flow. If I put pressure on both A and B, then this thing's going to center, and now we have flow. As soon as I have flow, it's going to shift that valve over, and my actuator don't get pressure anymore. So when both my inputs are true, my output over on my knot is going to be off, right? You understand? On the knower, if either input is true, and I send the output of that shuttle valve into a what? Into a knot, which is a normally open valve. If I send it into the knot, then that means if both my inputs are false, then my output's going to be true. If either input is true, the output's going to be false. Now, true, here when we say true, we're talking about pressure. So pressure is true, no pressure is false, right? And now that's the easiest way to explain logic. And we can do that in PLCs. We can do that when we use truths and false fault. In digital, and so, you know, in PLC, in program logic controllers, we do logic. But we do logic with wiring relay contacts, or contacts that make a circuit, And we can wire them AND, we can wire them OR, we can wire them NOR, we can wire them NAND. It just, once you understand when all inputs are true and that kind of stuff, it makes it a little easier to understand a logic. And you can understand why we need to do logic. Why do we need to do logic? Well, sometimes we need to compare things, you know, pressure here, pressure there. That's what exclusive ORs and exclusive NORs do. But that's a combination of logic circuits. We have to figure. Go ahead.
So the only thing I'm asking, for everything you got in PLC, you got a equivalent in that.
For every control system.
Every control system, you got equivalent.
Well, basic electrical circuits too. So electrical circuits, we can get more. So, you know, I can come up and I can have a bigger horsepower motor. Right? You understand? But people got to understand work in equals what? Work out. And that's what people, it's hard to understand. Transformers in a power system don't change the power. Power in, so technically, if the transformers and everything was 100% efficient, and I'm at my house and I turn on a 100-watt light bulb, whoever's providing me power would provide me 100 watts. Y'all understand that? But if I can change the force, I can lower the speed. Y'all understand that? So if my force goes up to transmit that power, the speed's going to go down. Well, what we do in electricity is we raise the force, which is the voltage. We raise the voltage. So this thing we call current does what? Goes down. And how much opposition a pipe exists is how fast we try to move things through it. So every conductor has opposition. And if you put current flow through opposition, you get pressure loss, which they call it line loss. So the lower I can make the speed, the less line loss we get, right? Does that make sense? So what they do is they step up the voltage to thousands of volts to transmit it. And then when it starts getting close to you, they start lowering it down for the safety. They don't change power. They step the voltage up. If they step the voltage up, the current goes down. If they step the voltage down, the current goes down. That's what transformers. They don't change the power. If they was 100% efficient, if I put 100 watts out of it, I'm putting 100 watts in.
Okay, let me try to do this. Does voltage do work?
No, voltage provide. We cannot do work. We have to have two things to do work. What's the two things we have to do work?
We have to have something in distance.
We have to have force and speed. That's what we use in electronics. Force and speed, and we call it watts. So if power is equal to V times I, so that's we do in electronics.
Okay.
Well, then I would be equal to P over V. If I transpose that formula. So that means if power does not change, if my power in and power out is the same, if I raise the voltage, the speed goes down. So if voltage goes up, I goes down. If I goes down and I push that through opposition, then I don't get as much pressure loss. Alabama Power calls it line loss. That's how much loss of pressure you have in the conductor. Okay, you understand that? So if I could step that sucker up to 750,000 volts, I could send 750,000 watts of power with 1 amp of current. But I cannot bring 750,000 volts into your house. Right? You understand? I cannot do that. Because it's looking for ground. And ground, I think it arcs one inch for every 11,000 volts. So 750,000 volts, you're talking about, that's why your high tension wires are where? Way up, right? And they're They're far apart. Okay. But I got to start getting that down close to ground. So what do we start doing? We start stepping the voltage down. Well, if I step the voltage down, the current is going up to provide that power. Y'all understand that? So I got to use larger gauge wires.
Okay, well, I guess what I'm trying to understand exactly, when we have that transformer and it takes that 24 volt and make it talk to that 240,
Well, the 24 volts would be a lot more current. So if I'm trying to send you 1,000 watts of power, okay, and I do that at 20 volts, if I do that at 24 volts, then that's going to be, how much current would that be? That'd be 1,000 divided by 24. Okay, you understand? Now, if I run that through a transformer and step it up to 200 volts, that's going to be 1,000 divided by 1,000, which would be 1. And that's what people don't understand. Work in equals work out.
Right, because I know they don't supposed to be touching. So I guess what I'm asking with that magnetic field effect on the other one, because I know that would show that gap in between when we transfer.
No, they spread them out, not because of the magnetic field, because of the push. Now, anytime you push a current through a conductor, you create a magnetic field.
Right.
If a magnetic field cuts to another conductor, it will try to induce the voltage into that conductor.
Right.
The amount of voltage it induces that conductor depends on the number of the strength of the magnetic field plus the number of loops in the conductor. Those conductors don't loop. Those conductors are straight. So the amount of EMF you get would be depending on how far they're apart. So that's why they separate them so far. Now, the less voltage or the less current, and current is what sets the magnetic field. It's not the voltage.
Okay.
The amount of magnetic field you get has nothing to do with the voltage. It's how much current you push through a coil. Okay. So if they can lower that current down, like I said, at 750,000 volts, how much current would that be? For 750,000 volts, I can send 750,000 watts of power with 1 amp of current, which means the magnetic field's not hardly doing anything. Right? You understand that? So how does transformers work? Well, they have tons of wires, and they put the wires directly together, and they couple them with magnetic coil. We don't need to be talking about this. Let's go. Let's take a break, guys. And Franklin, if you want to talk more, you can waste your break, and I can talk longer.
Because, so I guess in the back of my mind, I know there's a step up. When the transformer
The step up raises the voltage and lowers the current. Step down lowers the voltage and raises the current. So what is all your high wattage loads run off that you have?
Well,
we have 2 voltages in our house.
Right. 120, you got 240.
Okay, what is the 240? What runs off the 240?
That's your washing machine?
No, washing machines don't use run. Dryers do.
Dryers,
electric stoves,
dryers,
electric water.
got heat. Right. Okay.
Why do they do that?
Because they need more energy.
No.
Produce heat.
No. Because you're trying to push people on. You're trying to. What bill do you pay every month? You pay a voltage bill. Well, what do you pay? You pay a power bill. They don't call it a voltage plant, and they don't call it a current plant. They call it a power plant. So every load is rated at a certain watts.
Right.
The higher I make that voltage, the less current is going to require to push that watt. So that means that if I use a higher voltage, I can use smaller conductors. I can use smaller conductors. You'll hear people say that all the time. 240 is more efficient. No, 240 is not more efficient. You're paying for watts, right? You understand? But now instead of running 4-gauge wire back here, I can run 12-gauge wire, right? You understand? And run that load. Now I can run that wire through the beams of my house without running them through the ground, right? You understand that?
Okay.
I can pull that wire now. So higher the voltage, the cheaper it is to install and maintain.
strictly the area. I got confused with the area. The other sheet saying area was force divided by pressure. That's
No, area is not equal.
I mean,
Oh, yes, you're right. But area is equal force divided by pressure. That's exactly right.
I didn't have to.
That's if you know force, if you know pressure. You got to know those two things before you can calculate area.
Okay.
The formula for area is equal to the diameter squared times 0.785.
That's why I got thrown off there. See, it's a five times weight, and it's equal. It says 4. Do you have to always have to do weight? You have to do 5. The last one says 4. It says 4 diameter squared.
Yeah, but you got to understand. So let's say, and this is why I like this formula. So if area is equal to r squared times pi, okay, you understand. Well, the problem is when they give me the bore, they don't give me the radius, they give me the area. So area would be equal, if I use the diameter, it's going to be divided by 2. That gives me the radius, right? I can square that, and I could say times pi. Okay, that's the same thing. It's the same answer. I can go ahead and square this, but remember, this is over 1. I can go ahead and square that.
Right. Will I be able to use this?
Yeah, that's what I'm showing where it come from. So I could say, okay, I can go ahead and square this. So it's going to be the diameter squared divided by 4 over pi over 1, right? You understand? Well, let's come over here. Now I can come over here and say the diameter squared times pi divided by 4. That's exactly the same thing. And what's pi divided by 4? 0.785. So to save us a bunch of work, we can say area is equal to the diameter squared times 0.785.
That's all I want.
But if you do that, you'll come up and get exactly the same thing.
All right.
And that's what we talked about in class. But what they're doing in that thing is they're calculating the whole thing out. But if you did it, you'd come up and get what? If you did pi squared, you get the same answer. So what you do is you'd have to take the diameter, you divide it by 2, you square that, multiply by 3.14.
I would say something about sometime before that isn't the 1.75. If it's not square, that's pi. Square is pi.
What do you mean? The bore, if they give it to you in square inches, that means you don't have to do anything. If they give it to you in inches, that means that is the bore. You got to find the area. Now the rod side, you got to take the bore minus the bore area minus the rod area. Right?
Rod.
Yeah. And unfortunately, that worksheet don't have any of that on. Oh. But it was on that other worksheet where they gave you the area. That makes sense?
Yeah.
Okay. I ain't done row yet. See why we do these at the same time. So hydraulic valves are identified by the number of ports, which we call waves, a number of control positions, 2, 3 positions, type of control element, a poppet, spool, or disc, method of operation, mechanical, electrical, manual, or pilot pressure. The only big difference, and we can look at this is comparing hydraulics to pneumatics. So we start off with the number of connected ports. You know, it's exactly the same thing on both. It says the number of control positions. It's the same, exactly the same way on both sides. It says the type of control elements. It's exactly the same way on both sides. And the only little difference you see right here is this says 3 or 4. This says what? Then it says mechanical operation, mechanical method of operation, mechanical, electrical, manual, or pilot. You see that's exactly the same thing on both sides. So what we have in pneumatics is we do have a 5-way valve. We don't have a 5-way valve in hydraulics that I know of. I've never seen it. We do have a 5-way valve. We have 2 exhausts. And explain that, right? Why do we need 2 exhausts? Huh?
One that when it goes in and one that goes out.
Well, the problem is that normally they'll mount the exhaust on one side, and so one of your exhausts is going to have to go through a tube to come all the way out that side. And anytime you go through something, you're going to have what we call back pressure, right? You understand? So the advantage of having 2 exhausts is you eliminate back pressure. So each position has its own exhaust. And so you're not exhausted through it. One of your sides are not exhausted through it too. And what we're trying to do is help prevent back pressure in the return. Now understand back pressure. So anytime I send fluid flowing through a pipe, then the pipe's going to give us some opposition. And we will have pressure loss. We call that back pressure. So one of the biggest things besides the three-way 3-position valve, have some of our 3-position valves have, or even 2-position valves might have 5 ports. We've got a couple of them that's got 5 ports, right? So each of your working positions out there have their own wall, have their own exhaust. The biggest difference is that on pneumatic valves, they don't give these centers on a 3-position valve. They don't give, and this is the one I added. I found this the other day. So if you got this PowerPoint and you're looking at it off a Blackboard, this is not going to be on there. What was so neat about this is this really shows what a solenoid pilot operated valve does. So can you see it? So here's my solenoid right here. And this would be the same thing on hydraulics too. Now, what advantage of a solenoid over manually operated? You don't have, we can automate it now, so we can make electronic devices like PLCs and stuff like that, shift that spool instead of me going out there and pressing a button. Unfortunately, we didn't get any solenoid package for our fluid power because it costs so much money to go through. So all our valves are either pilot operated or manually operated or automatic operated, like your shuttle valves and your dual pressure valves. You don't have any, those things shift automatically, right? And check valves. Well, what they're doing here is they're showing me this right here is the solenoid, but all the solenoid does is move this little old plunger. Now here's pressure sitting right there, and it's ready to move through the spool. But if we follow this little old path right here, it comes over to right there. So when I energize the solenoid, it pulls this thing back. Then this come over here, and it's the actual pressure that pushes the wall, the spool. So here we can have a little old tiny solenoid because it's controlling just a very small flow. That's all it's doing, right? You understand? And it's got a little old tiny surface area. Since the surface area is so small, even though we might have a lot of pressure, the surface area of this thing is so small, it's not going to react with a solenoid. So now my little tiny solenoid can control a pretty good sized valve. And we call this pilot, we call it solenoid pilot operator. That makes sense? And so a lot of your valves are done this way, especially in hydraulics, because hydraulics, you got so much pressure, and you're trying to shift that spool against that pressure. Well, why not let the pressure do it for us, right? You understand? We got all this pressure out there. You know, this is what we call a pilot. Can y'all see that? So this is the actual solenoid. This is representing the coils of wire up here for the solenoid. You know, that's all that does. And this would be a pilot operated spring, a pilot operated spring return. And there's the spring over here. And a lot of your valves, this right here will be actually capped off with a screw, which is pretty neat. And so what you do is that in the solenoid, just mount on the side, so you can have a body, a valve body, and you can put a spring into the side of it, or you can put a solenoid in there. You can put the solenoid in there. So you decide whether you're going to manually operate the valve body, whether you're going to operate with a solenoid, the valve. So these companies make valve bodies, and then what you clamp onto the side depends on how the thing operates. You know. Are we okay? And we can see if we was over at the amateur line, you can see the valve bodies are exactly the same, but they'll have a solenoid on one side, and you looked on the other side, it'll have an Allen wrench going, and what's in there? Well, it's a spring. So what they've done is added that solenoid with a spring return. And you'll see two solenoids on both sides, but the valve bodies themselves look what? They look identical. So, and it only makes sense. It's like buying options for a car. You know, everything out there is almost the same. All the fittings, everything's already there, and they just add stuff to it. Normally, the wiring harness is the same. You ever looked at a car and it's got some wiring harness and just got some plugs out there that's not connected to anything? What do you think that's probably for? Some type of add-on or some type of option. So they don't have special wiring harnesses for this or that, and that way they can make them all the same. So one of the big differences we have with three-position hydraulic valves is they give those centers names. So these are both lever. These are all lever operated, and this is really good so you can see the spool. But this is a three-position valve. It's a three-way valve, right? Okay. But they call this a closed. They call this a closed set. Now, normally on a three-way valve, the normal position is the center position. So what would a closed center do? So so here we're calling them P. What does P stand for? This is a hydraulic valve. So P stands for pressure. T stands for tank. So that's your return. That's the port that takes it back to the tank. Then your working ports are called A and D. Okay, does that make sense? Do you ever notice how many working ports we have? We either have one working port or we have what? Two. Because what can we do with an actuator? We can make an actuator run in one direction, or we can make it go in two directions, right? You don't understand that. So all the working ports we have are two. Hydraulics, they name them A and B. So what would happen is this one would allow the pump to maintain pressure, right? You understand, and the actuator would be locked. What do I mean by locked?
It won't move once it gets in it.
Yeah, or it won't move if you stop it in the center. You see these big old earth movers, you know, out there, and they'll drop it down a little bit and they let go of the handle. It'll stay right there because once you move it back to that center position, the actuator's locked because the pressure, the fluid in there can't move, right? You understand? So we call it this would lock the actuator. And if this was hydraulics, guys, and you had no leaks in that system, you could not move that thing. Pneumatics, you might move it a hair, but you're not going to move it much because the problem with pneumatics is it's spongy, right? You understand? So a closed center, this would lock the actuator and it would maintain pressure on the pump. So now we could use that pressure somewhere else. This is called an open center. What would this do? This will allow the actuator to float, which means what? You go up there and grab that sucker and you can move it back and forth with your hand. If it wasn't this big, you know, just a regular actuator, you can move it back and forth. And it would bend the pump. The pump could not build up pressure. So this is something we might do if I wanted it to float, I didn't want to lock it, right, understand, and I'm not going to use that pump anywhere else. So if all I've got is one actuator out there, we don't want the pump trying to build up pressure in our system all the time, right, you understand? So this is called an open center. This is called a tandem center. Can y'all see what this is going to do? So this would lock the actuator and the pump would build up pressure. So this would be a situation where I've got one actuator and I want it to lock, and then I don't want my system to be under full pressure all the time. So the pump goes directly back to the tank, right? That makes sense? And then we have what we call a floating center or float center. Here we don't vent the pump. The pump maintains pressure and the actuator will float. So unlike the pneumatic valves, in hydraulic valves, we've only got how many centers? We got what? 1, 2, 3, 4 centers, and then garbage. These are just garbage. But these are the main centers that we have in hydraulics. We get into pneumatics, we get into these 3 position valves. Directional control valve, 4-2-way, don't tell us what that do. Direction with the closed neutral position, exhaust neutral position. So here they don't call it floating. It's the same thing, but they call it what? Exhaust neutral position. You see that? Yes or no? I'm right here if y'all wonder what I'm at. Where's that? We're looking at the 3 position valves. It could be right here. This one right here, they call this a closed center or closed neutral position. You okay? This is a closed neutral position. That's a 3-way valve or 3-position valve, excuse me. And then this would be a exhausted neutral position. So that means the actuator, what could you do with the actuator right here? Now on pneumatics, we're not going to ever vent the compressor. Because in fluid power, on liquid, you create pressure as soon as you want to use it. If I'm using pneumatics, what do we have to do first? We have to compress it. So you'll never see a vented, you will never see, in my experience, you'll never see a vented center where it vents the pressure, where the pressure is vented. You always block it off if we're not using it. You'll lose it. And then when you shift it over, what would you have to do? Wait till it recompressorize. A hydraulic pump, though, it's creating so much pressure when it's trying to create flow. When it works against something, you got to understand these guys don't create pressure unless you work them against something, right? You understand? So that's what we do with pneumatics. We work it against the whole system itself, right? Hydraulic pumps, though, you got 2,000 or 3,000 psi available to you on that sucker if you regulate it. Basically, if you don't regulate it somehow, that pump's going to try to build up as much pressure as it possibly can, right? You understand? So we regulate hydraulic pressure a little different. We use what we call a pressure release valve. So on a pneumatic system, we use what we call a pressure regulator. On a hydraulic system, we use what we call a pressure release valve, which means it vents it vents all the pressure above what you want, and it sends it back to tank. So with a pressure relief valve, if you set it at 3,000 psi, it would do what? It would start venting everything that tried to get above 3,000 psi, but where we didn't have to go back to the tank. So in pneumatic systems, we use a pressure regulator. On hydraulic systems, we use a pressure release valve. On both systems, we have what we call a safety release valve. What's a safety release valve? If you get too much pressure, if you get to a dangerous point, it vents everything, right? You understand? And we run that on compressors too. So our compressors, if something goes wrong with our regulator, right, you understand, or my upper limit switch, I think they showed it on Mythbusters one time, where they actually defeated the pressure relief valve and they defeated the pressure regulator, and they let that compressor just build up pressure. What happened? It blew it up. Y'all see it?
No.
They had a little shack out there. They had it in, and it shot it out the top like a rocket. I don't know how far it went up there, but it was that wasn't on a compressor. That was on a water heater. So water heater builds up pressure too, right? You understand that with heat, which is pretty neat. So that's one of the biggest difference, guys. Is here basically we ask you what does that center do. We don't ask you the name because we got so many different names, right? You understand? But when we got a 3-position valve, where is the normal position or at rest position? It's going to be in the middle, right? If we got a 2-position valve, where's it going to be? To one side, depending on where you put your actuators at, right? You understand? Depending on what, so we still have what we call a normal position or reset position. So if we got a spring on it, it's usually opposite of the spring, and that's why all these diagrams here that's in the textbook, a lot of them are wrong. Like this one right here is wrong. Why is that wrong? And this is out of the textbook, guys. I don't know who did this. What's wrong with that? The spring's on the right, but they got your ports on the left. So they're showing, according to the port identifiers, they're showing it on the left, but that spring's going to push it to the right. Y'all understand what I'm saying? So this has got, these are identified in the normal position. Well, where's the normal position going to be on this guy? It's going to be with the spring. The spring is going to push it in its normal or inactive position. So it means this should be over here. So this A and this P and this E should be on the right. But the guy that drew it on the what? Left. So that's drawn wrong. This is drawn wrong. This is drawn wrong. This one's right. This one's right. This one's right. This one's right, because it's a 3-position valve. But see, even the guy that did this, for some reason, didn't understand that. So if you got a spring there, now if you got double operators, it's up to the system to determine which direction it is, right? What's your normal position? So if you got 2 solenoids out there, what's the normal position? Well, it's whatever position they put that valve in to start off with. So normally, if we're running PLCs, what we'll do is we have what we call a reset routine. So when you put it on, it'll shift everything to what it considers its initial position. So if you went over there and looked at the manufacturing line, every one of them's got a reset. You flip the reset. Well, what does that do? Well, that shifts all your actuators back to their start position. All those two-way valves. If it's got a spring on it, then your normal position is which way the spring is pushing. So those are drawn wrong. And this figure's in your book, right? Okay. So it showed y'all the pilot valves, showed y'all the names of the positions for the fluid power valves. But why we teach both these at the same time? Why? Very, very, very little differences. So we used to teach pneumatics and did our labs on hydraulics. But now we teach hydraulics and do our labs on pneumatics. Because why? Because once you learn one, so what's the difference with fluids? Well, fluids we don't have to pressurize them before we use them. They create pressure when you use them, right? You understand? Gases, we have to do what? We have to pressurize those, pre-pressurize those. We pressurize the system. So your tanks out there, all your valves are shifted, all your cylinders and everything are locked down. So you've got pressure in your whole system out there. You pressurize it first. But the problem is, as soon as one of those valve shifts or those actuator shifts, then you're going to lose a little pressure until and that's why we say pneumatics we call it spongy. But what advantage does pneumatics have over hydraulics. Cheaper, the system is cleaner. Hydraulics is more efficient, but it's a cleaner system and it's a safer system. Cheaper to install, not necessarily cheaper to run, because we got to keep pressure in the system all the time. On the hydraulic system, we could actually vent the pump if we wanted to, right? Are we okay? Any questions?
Question. Do we have a choice? I mean, do we use any kind of liquid that doesn't compress for hydraulic?
Sure. There's a system that runs water. Normally, if they run water, they'll put a lubricant in it. So you'll see they'll have white in them. So there are water systems out there. The biggest problem with water is what we call the coefficient of expansion. Water's really, it's the only liquid it's the only substance that I know that expands when you heat it and it expands when you freeze it. So we have problems using water in systems that are going to go through real wide temperature changes. I mean, like your car, why do you use antifreeze in your car? Well, what happens if you didn't use antifreeze in your car? And it would bust your block in your car, right? You know what I'm saying? Hopefully it knocked that freeze plug. Most engines have got that freeze plug out there that's supposed to punch out if you do exceed that. So that's the biggest problem we have using hydraulics. Fluid, oils don't expand and contract, they just get thicker. So in cold weather, they get thicker, their viscosity goes up, and then in the warm weather, their viscosity goes down, right? You understand that? And we say that liquids are uncompressible. That's not true. They do compress. It's just that we don't have the ability to measure it. We don't have the ability to measure how much those things compress. So normally we use oils. The oil in industrial applications, very seldom would you see water. You'd see oils, mineral oils. Most of the time now we use mineral oils. Used to we use all different types of oils. This was the problem we had with our Rex Raw system. When it came time to change it, we would have to have a hazmat crew come in to change the oil in there.
Oh, mineral oil?
No, it wasn't mineral oil. It was rather hydraulic fluid. That was before they started going back to mineral oil. Most of them now use mineral oil now, but they didn't. They didn't use mineral oil. So the hydraulic fluids that they were using at the time was an additive. Had a lot of additives in it to add a lot of features that they don't do with mineral oil. And it was those additives that they stuck into it to cause it to be so dangerous. So that was one of the reasons we decided at that point to get rid of our hydraulics, and plus it's messy. You cannot keep a hydraulic system from leaking just a little bit. When it leaks, it gets dirty, and you see dirt all over the place, and it's caked up. And anybody that's worked around a hydraulic system see that. You know, seals, you got to have really good seals. There's no such thing as a perfect seal around all your actuators and everything. So if we have a leak in a pneumatic system, it's not near as bad, right? You understand, or air system, because you lose some pressure because of it, but still you've got a really good degree of operation, and it's not dangerous either. No, let's get around 600 psi.
Have you ever used vegetable oil?
I'm sure vegetable oil would be fine. I mean, usually they still put additives in there, but the advantage of oil is what? It lubricates the whole system. Is what the advantage. And it don't expand and contract. But you still got to worry about viscosity. So if you was up in Wisconsin, you would not use the same hydraulic fluid outside that you would use down here in Alabama. So they give you different viscosity. It's just like you used to, years ago when you put oil in your car, you put one weight in there, and then the car wouldn't crank in the wintertime because the viscosity was so couldn't turn it on. So what we do now is we use multiple viscosity oil. We use a real light oil that helps us in the wintertime, and then we use a real heavy oil that helps us in the summertime. So those dual viscosity oils now really makes a difference on our engine lives. Are we okay? So most of us run like five ASW weight for 530, 530 or 540 in the cold. Yeah, the Harley ran 50. So you get out there in the wintertime. And so you charge your battery. So you had your trickle charge. If you're running Harley Davidson during the wintertime, you put a oil on there every night. Put a little trickle charger on your battery. Because that oil is so dang thick that if you didn't have a really, really good battery, it would. My neighbor had one that it still had a Kickstarter on it. His bike was rude. You get him out there in the summertime, that thing to cry. And then finally get his truck go to work. And then you come back in the afternoon and it'd crank up. Anyway. So y'all okay? This is valves, guys. So and I think the next thing we're going to look at is what's our next lecture we'll look at? Next class? I think the next in the line is cylinders, yeah. Or it's cylinders, but what we're going to do is we're going to talk about actuators. The book basically talks nothing about cylinders. So what we'll do is we got different types of actuators. And we'll talk about more different cylinders that you'll run into than what the book has covered. The book only has a very limited running of what they talk about, but they're all basically the same.
Do we have those different actuators here?
Unfortunately, no, but you've seen them.
I understand.
Well, some of them you've seen, but some of them are so easy to understand that you don't. If you understand the way a single acting cylinder works, and you understand how a double acting cylinder works, and you understand how a cylinder works, right? So we have dual piston cylinders, we have double rod cylinders, we have rodless cylinders, we have, which the book don't cover. If you're going to run into rodless cylinders, we have, in fact, we showed y'all some over there, we talked about those a little bit. We have telescoping cylinders, which basically what they use on dump trucks and stuff like that. Have y'all seen those things? You know what I'm talking about? You seen them right? Telescoping cylinders, what we're looking for is we're looking for a cylinder that's very small, but it's got an extremely long stroke. So what they'll do is they'll start off with a big old bore, and then they'll put another cylinder inside that, and then they get smaller and it comes
And that's
up.
called what?
It's called a telescoping cylinder. So you start pushing, and it pushes against the bottom. When that gets out, and it stops, and you move to the next surface area, and it'll start pushing until it does what? Until it bottoms out. And then you hit then you hit the other one, and it stops, and then you start pushing on a smaller area, and it comes out, and you can get extremely long strokes. But like you said, I've seen people that's had those things overloaded, and it tips over and it bends those things. Yeah, because you get those things fully extended. Yeah, the smaller rod is, and if that weight starts shifting, it'll bend those rods, and basically, I've seen it flip these trucks over too. I've seen them flying down the interstate too. There's a video with it bent up on the back. Yeah. Okay, guys, y'all take a break, and then we'll come back and we'll laugh. Oh no, we'll come back and go over some more laps. How many laps did we go over? 3? Okay. We'll go over some. I think we have up to 5 that we connected with. So let's go take a break. It don't mean you got to do 5 tonight, because then we're still working on 1. But we always like to stay ahead of the class, right? And so that way, odds are it's going to be hard for you to leave early, unless you get to the end of the semester. Once you get to the end of the semester, and you've done all the labs, then you'll have to come back to the troubleshooting lab. Okay, I'll take a 10-minute break, guys.